Let me introduce the expert for today's session. The HSC expert and Mr. Aniket Vesaikar are going to be presenting this particular session. HSC joined the healthcare engineering field in 1971 after graduating from the 14th batch of ARC Mechanical Engineering. He has completed his Masters in Mechanical Engineering with specialization in finely electrical from IIT Kanpur, and he has been working in the area of structural mechanics for a very long time. He has more than 60 publications to his credit. Second expert is Mr. Aniket Vesaikar, who has completed his bachelor's in aeronautical engineering and master's in mechanical engineering in machine design. He is currently working at SVR Infotech as a CAE support engineer for more than 4 years, and his work includes machine structural analysis, tech preparation, quality work, and so on. I would now like to request both the experts to start with the session. Over to you, sir, and Mr. Aniket. Go ahead.
Aniket, can you make the slides now? Good morning to everyone for the dynamic analysis using FEAST. Okay. Aniket, can you show the first slide? Aniket?
Yes, sir. Yes, sir. Is it visible?
No, it is not visible. I am not able to see.
We are able to see, sir.
No.
Sir, you can go to the list of participants.
Okay.
So you can click on list of participants, and there you can pin to my name. It will be visible, sir.
List of participant. Okay.
There I have 2 accounts. Can you see there I have 2 accounts? Or else, sir, hello. Just
hello,
a minute.
hello.
I'll stop the screen sharing and I'll share it again so it will be visible. Just a moment, sir.
Okay.
Now is it visible, sir?
No, I am not able to see anything.
Okay. So right now, what is there on your screen, sir?
It is coming join with code and example. Yes, now.
Now it is
Now it is okay?
Yes, sir. Yes, sir.
But there is no screen.
Okay. Okay, so at the bottom, can you see the list of participants? Like there are 23 members currently in the meeting. You will just click on that 23.
Yes, I have clicked.
Now there is list of participants. So there I have 2 accounts. Now you will see the list of participants. There I have 2 accounts.
Yes.
There are 2 accounts. So you can click on the 3 dots are there on the right side of that. Right side
Your
of my
name.
On the right side of my name, there are 3 dots, vertical dots. You click on that and click on pin.
Click. Pin. Okay.
Is it visible now?
Now you are visible now.
Okay, no issues. So similarly, I have since I have 2 accounts, so you can click on another account, and there you click on vertical 3 dots and pin it.
Acha, there is somewhere else we have to now press.
So now since I have 2 accounts, now it is visible.
Now it is alive.
Yes. So we can start, sir. Yes.
Okay. Thank you.
Thank you.
Now it has gone. Okay. Now the type of analysis depends upon the kind of excitation. For example, we have shown harmonic analysis. This may be one example I can give is rotating machinery. This may be due to rotating machinery. Then periodic vibration may be because of the wind by the flowing around the structure. The base excitation is normally due to earthquake, and similarly the transient vibration can be due to shock loading, which can be due to the vehicle crash vehicle, the blast loading and impact loading. So there are a number of type of excitation which govern the what kind of dynamic analysis we should do, whether it is a harmonic analysis, whether it is a periodic vibration, whether it is a base excitation or a transient vibration. Now we will like to first define what is a single degree freedom system and what is the multi-degree freedom system. In the single degree freedom system, we have one spring and one mass system, which I have shown in the figure. Is a vertical one spring and mass system, which is moving, mass is moving up and down. Similarly, on the right hand side, it can be a horizontal spring and a mass, and the mass will be moving left and right. Here only one coordinate is necessary to describe the equation of motion, and therefore we say it is a single degree freedom system. If I have multiple masses and multiple springs and they are connected in series, and if we are pulling them, if they each individual masses has its own degree of freedom. This is the and here, for example, we have three masses. Three masses can move independently in different way by and therefore it is a 3-degree system. If the masses are more and springs are more than 2 masses and 2 springs, then we define it is a multi-degree freedom system. Next slide, Aniket. Now the classic example of a single degree freedom system is a elevated water tank, which we have shown in example. And if it vibrates, then it can move on the right hand side, it can move on the left hand side to a given amount of vibration amount. This can be represented, the movement on the right hand side and movement on the left hand side can be equated as a spring mass system. It is a mathematical model of this is elevated water tank is a spring mass system where the mass is moving left and right. So in the elevated water tank, the assumption is the mass is situated at the top and the column has only stiffness. The column mass is negligible compared to the mass of the water tank. Okay, so we have a spring which gives the column stiffness and a elevated water which act like a mass, and that is the way I have represented the spring mass system. If I look the free body diagram of the mass system itself, if I look the free body diagram of the mass system, then you can find out the various forces which are acting on the mass. They are the inertia forces, which is nothing but mass into acceleration, equal to m into x double dot. Spring forces, which is nothing, they are the elastic forces. It is nothing but stiffness multiplied by the displacement of the mass, which is k into xt. And the damping forces, the damping coefficient multiplied by the velocity, which is nothing but c, which is damping coefficient, into x dot. Okay. Now this equation, the equation of motion can be written as is mx double dot c x dot plus k x equal to the external force ft, which I have shown. Okay. Now this equation which I have written here This is the equation of motion of the mass m. This can be derived using, there are four ways we can derive: using Newton's second law, D'Alembert principle, Lagrangian equation, Hamiltonian principle. In fact, all these should be taught in the engineering colleges by the professor, that they should derive this equation using Newton's second law, D'Alembert principle, Lagrangian equation, and Hamiltonian principle. And they also describe what are the differences between these three, where I can use Newton's law, where I can use D'Alembert principle, where I can use Lagrangian equation, where I can use Hamiltonian principle. Okay, the free vibration equation can be written by substituting the damping equal to 0 and the external force equal to 0. If I substitute these two in the above equation, the equation gets converted into mx double dot plus kx dot equal to 0. Aniket, next. Okay. Now, if I divide by mass, then I get the x double dot plus k by m into xt equal to 0. Okay. Now I can assume that the omega n is under root k by m. This is a constant I am assuming, and if I substitute in the equation, the above equation, we get a equation x double dot plus omega square x equal to 0. Okay, here I am not, there are x double dot and x, they are the function of time only. And since it is a single degree freedom system, we get only one variable, which is the x1, the one equation. Okay, this equation is a simple harmonic motion. Okay, the angular frequency can be written as, or circular frequency, what you say, this is also known as angular frequency or circular frequency, is a omega is equal to under root k by m, and this unit is radian per second. Similarly, the linear frequency can be written as omega over 2 pi, and the unit is a cycle per second or hertz, and the period, which is nothing but t, equal to 1 by f, is the unit is a second. Also, we also write the f, which is nothing but the linear frequency, is the number of oscillation or rotation in a given period of time. Okay, the next. Okay, so the omega can be written as what we have written under root k by m, which is k by, or mass can be written as the weight divided by g, and the weight divided by g is nothing but the static deflection. So therefore, the omega can also be expressed in terms of static deflection of a structure. Omega equal to g by the g by static deflection under root. Okay. Now, the static deflection can be calculated very easily. We know the load which is acting, or the weight which is acting on the body, divided by the stiffness of the structure. Okay, next, Aniket, next slide. Okay. I think we have missed. Can you go back? One slide is, I think, okay. I think there is something missing which I find here. Okay, this can also be written as a t period, because the omega and period, they are connected. 2 pi under root delta static deflection divided by g square root. Okay, and therefore the t period can be written as a constant c into square root of static deflection. C is a constant which is nothing but 0.32. If delta S is calculated in deflection is calculated in inches, then period is equal to the square root of deflection divided by 3. This is a very simple example one should remember. for getting the first fundamental frequency, if you know the static deflection, and if you take the under root of static deflection, divide by 3, that will give the period, and from the period one can calculate the frequency of the structure. Okay, next. Okay, I think there is one slide which is missing, because this is in case of okay, before you go, there is something इसके पहले नहीं, ये तो स्टैटिक डिफ्लेक्शन ना, दिस इज ए केस ऑफ क्लैम्प्ड यूडीएल. Okay, I think there is some problem in slides. Okay, let's assume example I am giving here, a clamped beam, both hand fixed, is loaded with the weight at the mid span 7,000 pound, and if the length of the beam is 200 inches, E equal to 13 to 10 to the power 6 psi, I equal to 400 inch square, which is moment of inertia. Determine the fundamental frequency. So for this problem, we can find out concentrated weight is given, which is nothing but 7,000 at the mid span. So we can find out mass, which is nothing but weight divided by G, and which comes out to be 18.12 pound per pound second square divided by inch. The stiffness can be written as 192 EI over LQ, which is nothing but 288 into the power 3 the pound per inch, and the circular frequency omega is calculated k by under root 1.26 radian, 126 radian, and frequency can be given in 26 TPS hertz. The period can be written as 0.05. So this is one way of doing that. If you know the structure with boundary condition, we can calculate the weight. Now in this, it is assumed that the clamped beam has a stiffness only. Mass is concentrated at the center point, which is nothing but the weight. Okay, next. So we can calculate the frequency. Now this now we are trying to calculate the normally the equation which I have written, that is a single degree freedom system. In multiple degree freedom system, the above equation can be a mass matrix multiplied by the acceleration vector plus stiffness matrix multiplied by the displacement vector equal to 0. This is the equation of free vibration equation of multi-degree freedom system. Now using the finite element computer program, we normally calculate the masses as a lump mass or consistent mass. So we should know, if I am using the lump mass system, what is the frequency? If I am using consistent mass, what is the frequency? So this example I am showing is a bar. It's a bar, it's not a beam which is shown as a vertical force. Bar which has a lump mass. So I'm considering only one element. So stiffness of the bar is AE over L, 1 minus 1 minus 1, 1, U1, U2. U1, U2 are the deflection at node 1 and node 2. Similarly, the lump mass is equal to the omega square into rho AL. Rho AL is the total mass of the beam. The rho is the density, A into L is the volume, volume multiplied by the density is the mass. It is a mass density we are talking about. And half it is lumped at node 1, half it is lumped at node 2. The equation which you are seeing in the presentation is a standard eigenvalue equation, where we write omega square mass matrix into the displacement vector equal to the stiffness matrix into the displacement vector. Okay, this is the standard eigenvalue problem which I will explain later on. Okay, since node 1 is a fixed, so we apply the boundary condition at the node 1. If I apply the boundary condition, so I can delete first row, first column of this equation from both the sides. If you delete this, you get this equation A over U2 equal to omega L square rho A L divided by 2 into U2. Okay. By applying the boundary condition, we get this equation, and from this I can find out omega L, which is nothing but the circular frequency when I use lump mass system, is a 2e over rho L square, which is 1.414 divided by L e over rho, which is the density, the mass density. We can go to next. Okay. Now, if I use a consistent mass, so I have to only change the mass matrix. The stiffness is same. So stiffness is the mass I am writing. This is the again a standard value problem, standard eigenvalue problem, where stiffness into the displacement vector equal to omega square mass into the displacement vector. So the consistent mass is rho L over 6, 2 comma 1, 1 comma 2, U1 U2. If I apply the boundary condition at the node 1, apply. Yes, similarly, the first row and first column from both the sides, they are deleted. If you delete that, you will get the equation which is A over L multiplied by U2 equal to omega square consistent mass. CONS means consistent mass matrix. The frequency which you will get is corresponding to consistent mass when I am using. Rho L divided by 6 multiplied by 2 multiplied by U2. From the omega consistent I can calculate, which is nothing but 1.732 divided by L E over rho. 1.732. The exact solution for a fixed beam is 1.571 E over rho under root. Here L 1.571 divided by L is left, which you can correct it. Thus, it shows that consistent mass overestimate and the lump mass matrix underestimate the interior frequency. This gives a idea that the consistent mass calculate the natural frequency which is higher than the exact one. Lump mass calculate the frequency which is lower than the exact one. So this is the idea which comes from a bar vibrating axially. Okay. Next. Now I can use two element, and the same kind of conclusion can be drawn. Here the two element is stiffness matrix, which I have shown a symbol, and on the right hand side a symbol two mass matrices, two element mass matrices. And now first row, first column is deleting from left and right. You get two equations here, and if I solve that equation, next, Aniket, next one. If I solve this equation, I get a omega 1 and omega 2, which is 1.531, 3.695. The first fundamental is lower and second fundamental is higher frequency. Now, one thing is clear in this, that if I want to have one frequency, then even entire bar you can model as only one element. If you want more than one frequency, then you have to use two elements for two frequency, three elements for three frequency, four elements for four frequency. For higher, if you use large number of element, you will get the frequency which is more than one, more than two. Okay. Next. Similarly, consistent mass two element I am using, and same way applying the boundary condition at node 1 and assuming lambda equal to rho omega L square divided by 24E. If you substitute it, then you calculate. Okay. Next. Aniket, next. Lambda 1 is equal to 0.108, lambda 2 equal to 1.32, And omega 1 you can calculate 1.61, omega 2 5.63, and the exact one is I pi 2l E over rho, where I equal to 1, 3, 5, 6 up to infinity. This also shows two mass matrix. If I assume two element, if I take it, it also says the same thing. The consistent mass overestimate the frequency and the lump mass underestimate the fundamental frequency. This also says the same thing. So this is true in case of one element or higher number of elements in a bar element. Okay, next. If I take a beam element now, instead of bar I am now using beam element and only one element I am taking. Then the stiffness matrix is this. This is a long long beam. Sorry, long beam. Okay, so it has a at each node it has a displacement and rotation, 2 degree freedom per node. Okay, so we have a beam which has a two node, one element. So it has a 4 by 4 stiffness matrix and 4 displacement vector, which is u1 theta 1, u2 theta 2. Okay. Next. Okay, next. Similarly, I can write down the lump mass. This is the lump mass for two elements for entire beam. And the equation, the case one equation is basically for lump mass, which is nothing but the standard eigenvalue equation. This is the standard eigenvalue equation, which I told earlier that I will let you know how to get the standard eigenvalue equation. If I illuminate the node 1 degree of freedom, which is nothing but u1 and theta 1, both we can eliminate, we can get equation omega equal to 2.4495 L square E over rho A. This is the first fundamental frequency you get. Next. If I calculate, take the consistent mass matrix, so only change is consistent mass matrix and illuminate at the node 1 u1 and theta 1. If I eliminate, you get this equation. And if lambda equal to, this is the equation which I am assuming lambda, then equation of eigenvalue can be found out. Okay, next. Is lambda 1 is equal to 0.059, 1.769, and then omega 1, omega 2 we can write down. Exact value is 3.52 L square. This is the exact value if you take a beam problem, first fundamental frequency. So in this also it says that the consistent mass overestimate the frequency and slightly, and the lump mass underestimate the frequency, fundamental frequency. So this is true whatever the structure you take. Lump mass is easy to consider it. Normally in calculation lump mass is used. But if somebody wants to tell that you should use consistent mass, you can use consistent mass. There is no difficulty. But one should realize that fundamental frequency is going to be overestimated if I use consistent mass. Okay, next. Now many times what happened that we have a in the industry, particularly in petrochemical industry, you will find you have a column, vessel, which is a thin vessel and a tall vessel, which is fixed at the structure, that is the ground. And we are supposed to know the fundamental frequency of this structure. So for this, the best way of calculating the fundamental frequency for the mechanical system, for the equipment I am talking about, one can calculate the period, which is defined as 1.79 omega L square. It is based on basically static deflection. This is based on a UDL cantilever beam. Since it is a thin, I am assuming I, which is nothing but the moment of inertia, thin vessel, cylindrical vessel. So I am assuming where R is the radius of the cylinder and T is the thickness of the cylinder. So pi r cube T is nothing but the moment of inertia. And the deflection The static deflection can be calculated. The mg is nothing but weight per unit length. L to the power 4 divided by 8 EI. So this is a static deflection. From the static deflection, we can calculate the period. You know the C under root delta S, one can see. Now, from there, the period can be calculated. And once you know the period, next, if you know the period, and normally in seismic design, the spectra is given. This is the spectra I am showing. The spectra is nothing but on the vertical axis, acceleration is plotted. On the horizontal axis, frequency is plotted. And this is a curve given by any earthquake person who generate the spectra at the ground for a given damping. This curve is a spectra for a given damping psi. So from this, once we know the period, I know the frequency. Because period is known, it means frequency is known. Frequency is known, then I can find out what is the acceleration. This structure is attracting this much acceleration. The structure means the mass is attracting this much acceleration when earthquake takes place. So what is the total force? If the W is the weight of the structure, the maximum force can be 1.5 times W by G multiplied by acceleration. Acceleration we got from this. And 1.5 is to account higher mode effect. If you have a, here the frequency is calculated from fundamental frequency, one frequency. But in the structure, we have a number of other frequency. To take the effect of other frequency, I multiplied 1.5. And this is the equation derived by ASME for the equipment design, that once you know the forces acting on the mass, I can calculate the shear force at the base, I can calculate the bending moment at the base, and both shear force bending moment can be used in designing the support structure. And this is in nutshell is done in the earthquake design. It's a very simple if you look from the design angle point of view. And normally the structure is converted into a single degree freedom system. Any structure you can convert into single degree freedom system, calculate from the equivalent static the maximum deflection. Once we know the maximum deflection, we can calculate the period of the structure, we can calculate the frequency of the structure. From frequency, I can calculate what is the acceleration seen by the mass. Once I know the acceleration, I use this equation. The maximum force is 1.5 into W over G into the acceleration. This is the force acting on the mass. So mass is most of the time, if it is a UDL, then it is a distributed. If it is a concentrate, then we put as a, just like elevated tower, we put the mass into multiply by acceleration, that much force at the mass level. Okay. Next, we can go to the next. Many times we have a saddle supported vessel in the industry. This can also be converted into single mass and spring system. And one can calculate the static deflection. And from static deflection, you can calculate the period. And from the period, you can find out the frequency. And then you can calculate what is the force coming at the base of the support of two saddles. Next. Next. Aniket, next. Then we have a many time skirt supported vessel. We have a vessel which has a skirt at the bottom, fixed at the bottom, at the skirt level. This also has a period formula given 7.65 10 to the power minus 6 h over d. H is the height of the vessel, including the skirt. D is the diameter of the vessel, and under root W d divided by T, where W is the weight per unit length, D is the diameter, T is the thickness of the vessel. Now here the weight per unit length, in which the metallic weight of the vessel, insulation weight, plus content inside the whatever the content which you are keeping in the vessel, all they are converted into weight per unit length. And from there you can calculate the period, calculate the frequency, calculate the forces, and then design it. If you have a leg supported vessel, same principle can be applied.
Yeah.
Okay. So this is a practical problem which I am telling
You
you
are creating a
how
character,
to
right?
solve easily
Was that done?
for the petrochemical and
So you
the
use
industrial equipment. Okay, next,
regular fish too.
next. Okay, this is a elevated tower where the period can be given as 3.6 WLQ over the EI, where 3 I have taken in outside. That is the reason why we get 3.63. Okay, next, next. Okay, now we are going slightly more detail about the earthquake excitation. If I have a single mass degree prism system, which is nothing but a column having a load, the weight of the water tank at the top, and if earthquake occurs, and this is connected with the ground, and the ground means this is connected, this is on the rock side. Below the column, we have a rock. So that is the reason why I am assuming it is fixed. But if you have a soil, then I can model as a soil stiffness, spring and mass, spring system. Okay. Now, if earthquake takes place at the ground, if the ground moves by acceleration time history, which is nothing but the representation of earthquake excitation, then entire thing they move to a amount UG, which is known as a vertical line I have shown with no the okay with horizontal displacement uniformly it is moving. Then it is bending, which is the third graph, which is bending like a cantilever beam, and mass is moving slightly right side. So you have a acceleration which is a uniform acceleration UG double dot, and you have a relative acceleration UR double dot. Okay. So if I assume it is equivalent to spring mass system, then the base where it is supported, that is moving first a uniform amount, and then spring is stretching. Stretch is given by relative stiffness. Okay. So now if I write the free body diagram of the mass, so I can write out a spring force, which is nothing but stiffness multiplied by relative displacement. Relative displacement. That is the spring force, which is elastic force. Inertia force, which is nothing but mass into total acceleration. It is U uniform acceleration, U dot G plus U double dot R relative acceleration. Okay. And the damping force, which is nothing but the damping coefficient C multiplied by relative velocity. So with the spring force, we have a relative displacement. With the damping force, we have a relative velocity. With the inertia force, we have a total acceleration. And on the right hand side, the external force is zero. If I add all these three and make it equal to zero, I get a equation. Next. Okay. Uh, Next, I can get a equation which is nothing but M, which is a single degree freedom system, U double dot G plus U double dot R, the bracket close, C UR dot plus K into UR equal to 0. And I can take it UG, uniform acceleration, on the left hand side. Then the equation can be written as M UR double dot C UR single dot plus K UR equal to minus M U double dot G. That is the uniform acceleration. And if I divide by mass, then I can write the equation UR double dot plus C over M UR dot single dot and K by M into UR equal to you get minus U double dot G uniform acceleration. This equation can be solved with the using finite difference method. Okay, you can solve it by finite difference method, and You can also use any Newmark, beta, Wilson, theta, number of methods are there to find out the acceleration, velocity, displacement plot with time, because they are all a function of time. Or we can use Duhamel integral. Duhamel integral is normally used in almost all code, because it can be used to integrate closely. Okay, next, if I integrate it, I get a velocity which is 0 to t, u uniform acceleration, e to the power minus j omega t minus tau sine t minus tau into d tau. And if I again integrate once, I can get the displacement. Now this is we get a displacement versus time plot, and if I take, it will be varying with time. If I take the maximum value only one value, then I can write the u is a function of time maximum value, which is written as sd omega into xi, which is it is a frequency of frequency and damping, which is a function of both frequency and damping. And sd is known as the spectral acceleration displacement. Similarly, I can define spectral velocity, spectral acceleration I can calculate, and all three are related by omega. All three are related by omega, and the we can write them, relate them, and express them, the spectral displacement, spectral velocity, spectral acceleration. And the total acceleration will be if I add uniform acceleration, because this is the relative one. Okay. Next. Now I am showing one example how to solve a single degree freedom system earthquake design problem. Okay. So I have a single degree freedom system, mass located at the top like a elevated water tank. It has a stiffness, it has a mass. The length of the column is 14 meter. The mass is 40,000 kg. The E value is given. The I is also given. Okay, and EI we can get by multiplying E into I. The ground spectra is defined. Normally it is given in the form of displacement versus frequency, but here I am writing a equation which represents a spectra for a given damping, 5% damping, which is nothing but SA over G equal to zero point 0.1 plus T e to the power 2T. This is defined in the form of equation. So I can use this equation to calculate what is the acceleration for a given period. And this is already given for a damping value for 5%. If you have a 2% damping, it has to be increased, and code gives how much from 5 to 2, how much factor you should multiply to get 2% damping. Stiffness is 3ei over L cube. We can get the stiffness value. The mass is already given, and if I take, then circular frequency is k by m under root 3.2575 radian. Omega I can calculate, square I can calculate. Okay, and the period I can calculate 1.93 second. 2t equal to 3.86, because we require e to the power 2t calculation. The frequency I calculate and period I can calculate. Okay. Then I can find out SA over G, which is nothing but 0.1 plus T e to the power 2T. So I can substitute the value of T, which is from the top 1.93, e to the power 2T, e to the power 3.86. And if I solve that, I'll get a acceleration which is equal to 6.42 meter square. G I have multiplied with this. So SD is equal to, this is the acceleration which is defined here. SD will be nothing but acceleration divided by omega square, because there is a relationship between the SD and SA with respect to using the circular frequency. So I can get SD will be this much. SD gets basically 31.5 inches, this much millimeter and this much inches I can get. This is the movement of the SD means the maximum displacement of the mass. SD means for single degree freedom system. This is the maximum displacement of the mass. Okay, next. Now that much acceleration we got 4 2. So I have a multiplied mass multiplied by the acceleration, that is the force acting. Now from onward, once we know the forces, onward is the strength of material calculation. There is no more dynamic calculation now. So simply base shear is same, and the bending moment is the force multiplied by 14 meter, that is the moment, and Z, the section modulus is I over C, I can find out, and sigma bending stress equal to m by Z I can calculate, and that comes out to 7.57 MPa. In this problem, I have assumed that column having the diameter is a circular column having the diameter 1 meter, the outside diameter and inside diameter 3.4 meter. This is what I have assumed in calculating the moment of inertia. Okay, so this is a very simple way of doing a earthquake design of a structure when we have a single degree freedom system, because in single degree freedom system entire mass which is situated, which is a 40,000 kg, is moving left and right at the top. Okay, next. Now something about Indian standard 1893, which is nothing but earthquake code as per the our Indian standard. There they design a seismic coefficient which is AH, which is nothing but Z by 2 multiplied by I by R, SA over G. Okay. Now, AH is a seismic coefficient. You will find what is the seismic coefficient and how it is used. Z is nothing but a zone factor. That entire India is divided into now 4 zones, and the Z value is defined at various zone. Now, IS also give the district-wise zoning factor in the tabular form. I is the importance factor depending upon the fundamental depending upon the interest of the factor. Means if it is a residential building, then I is one number. If it is a school building, then I is higher than residential building. If it is a police station, it is a higher number than residential building. It is a cinema hall. The how many people they accumulate here. If the structure collapse, how much the risk is. So depending upon that, I importance factor of the structure is defined. RJ response reduction factor
कोई लड़की
is
है
basically
जस्ट
depend upon
व्हाट
how
इज
much
दिस
cracking we are allowing. Because in the residential building,
कोई नहीं
we
उसको
allow
इतना
some
नहीं पता
amount of
रहेगा
cracking,
उसको
but no
बताना है कि
collapse.
चीज़ क्या है
So
पता है
various kind of residential building, because they have certain amount of redundancy.
आपको
So
मैंने वो
R
स्लाइड
value
दिया
is
था
defined by the code.
मतलब मैंने
I
एकदम
and
दिया
R and Z
दिखाया था
all
स्लाइड्स
defined in IS code. SA over G is a average
प्रेजेंटेशन मोड में है
response acceleration coefficient for 5% damping. Now, there are
प्रेजेंटेशन चाहिए
three
क्या आपको
kind of soil. India has been divided in three kind of soil.
सर को आप बोलेंगे
One
कि
is a
प्रेजेंटेशन
rocky
मोड
and
में है
hard soil,
तो कॉपी नहीं कर सकते रहेगा
rock type
ओवरराइट बोल
structure.
देंगे
Other is a medium soil site, and the third one is a soft soil, rock, hard soil, and soft soil. For the rock, that is center one, the SA over G is defined for a given period. SA over G is defined for a period. For the soil site, they have defined some different number, and the medium soil they have defined. Basically, if you see, the changes will be third line in the entire the for the rocky side. Actually, There was correction, but they have not made correction. 1.36 for the rocky side, it is not 1.35, it is 1 divided by T. And for the medium soil, it is 1.36, and for the soft soil, 1.61. You can see very well because whatever I am presenting, slide is made by Ankit, etc. There is some mistakes. So therefore, you should see the highest the standard for getting the exact number. Okay. The zone factor for zone 2.1, zone 3.26, zone 4 is 0.24, and zone 5 is 0.36. This is the Z value defined. Next. Similarly, R and I are defined. All are plotted in this figure. The hard soil rock is the first one, lowest one, and then the medium soil and the soft soil. All are in the form of period. Normally, one thing also you should note that for civil structure, acceleration is defined with respect to period. That is, they call spectra for 5% density. But for the mechanical equipment, we define on y-axis acceleration, on the x-axis it is a frequency, not period. To mechanical equipment, always we define spectra, acceleration versus frequency. For civil structure, they define acceleration versus period. Okay, because normally the civil structure people, they are very comfortable with period. Okay, next, although both are same. Okay. Next, go to the next. Design based shear, which is nothing but dB. So we calculate AH. Once I know, suppose if a tower is built with a mass single degree freedom system, and it is situated in Mumbai, then we know an R is defined. What kind of structure is there? We spin forces, these. So the Z is known, I is known, importance is known, factor is known for a elevated water tank, and R is also known. And if we assume it is a rock side below, then we fix the SA over G, also known. Using all these things, we can calculate what is the AH. And using AH, if I take the mass of the structure, mass of the weight of the structure, W, weight of the structure, then the base shear can be given as A multiply AH multiplied by the omega, W, which is nothing but weight, total weight, seismic weight of the structure. Okay. So this is the equation which is used in calculating the base shear, and then base moment also you can calculate. The equation of motion for a multi-degree freedom system, instead of one, it is a matrix now. It is a mass matrix, acceleration vector, the damping matrix, the velocity vector, plus stiffness matrix, displacement vector, equal to the mass matrix into the vector of unity multiplied by the uniform acceleration. Okay, this is the equation, and now here the x is a function of space and t. It is a function of x and t, both. Okay, so therefore, if I want to solve this, in the same thing we can do. Next, next, Aniket, so I can solve it using multi-degree freedom system. But if I want to calculate first fundamental frequency, then I can assume a mode shape, how it deforms in first fundamental, which is nothing but the static deflection. What is the shape of static deflection of a structure? So if I assume the static deflection, now I am assuming ux comma t equal to, it is a function of phi x, which is nothing but the now separation of variable I am using, which is a function of x multiplied by u is a function of time. One is a function of x, another is a function of time. And the function of x part, which is nothing but the mode shape, can be written as 1 minus cos pi x divided by ql in such a way that it satisfies the boundary condition. What is the boundary condition? At x equal to 0, it is 0. And at x equal to 0, again the rotation, the u dot is 0, u is 0, u dot is 0, both at x equal to 0, because it is fixed at the ground. Now, if I this mode shape is satisfying this boundary condition, both the displacement boundary condition and rotation boundary condition. If it is there, then I can use the Rayleigh quotient. Rayleigh quotient, which is nothing but omega n square equal to k star divided by m star, which is in case of distributed system. It is in case of distributed system, it is 0 to L ei into phi double dot phi double dash into whole square dx is divided by 0 to m psi square dx. If I integrate the numerator and denominator, I get generalized stiffness. I get k star for numerator and denominator the m star generalized mass. So generalized stiffness and generalized masses, they convert the system into a single degree freedom system. This structure becomes simply a k star and m star spring mass system, single degree freedom system, because I am calculating the only one frequency. Now, if I have a distributed system where we have a number of stiffnesses and number of frequencies, number of masses, number of stiffnesses, number of masses, multi-degree freedom, distributed multi-degree freedom system, then the K star can be calculated. We know that phi transpose, which phi is the mode shape, phi transpose T mass matrix multiplied by phi again matrix divided by the generalized mass is phi transpose T, the mass matrix into phi transpose. So the each will give you number of frequency, but if I calculate, I take only one mode, first mode, then the K1 star can be calculated at phi 1 transpose, which is a vector, multiplied by the mass matrix into phi is a vector. You get, if you multiply that you will get a scalar quantity, which is nothing but K1 star. Similarly, denominator, you will get phi transpose I, phi 1 transpose, m is a matrix, phi multiplied by phi is another vector. If you multiply these three, you will get the another scalar, which is m star. So we can get generalized stiffness and generalized masses, generalized masses to convert into the single degree freedom system. Yes, to convert into the single degree freedom system. So single degree freedom system can be converted from the multi-degree freedom system easily. This is the way we do the calculation for converting single degree freedom into the multi-degree freedom system. Okay. Next, if I get go back. If I next. So we know the K and M star. The K is 3.04 EI over LQ, which is simple 3 EI over L cube. M star equal to 0.03 ml. M is nothing the mass per unit length. L is the length of the column. So which is nothing but the M star, which is the generalized mass. And if I take next, 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 we can calculate the frequency using these two. Okay, we can calculate and simply the frequency period can be calculated and the forces can be calculated. This is a harmonic vibration example we are seeing. How to solve a harmonic vibration? So in that I am showing here, we have a cantilever beam. On that we have a machine of which is producing a force F equal to 200 sin 60. This is the excitation, the force. The cantilever beam has a mass of 2000 pounds per second square inch. This is the mass we are having. Length of the beam is 100. E is defined, I is defined, area of cross section is defined. and the length is defined. Okay, the width of the beam is 6 inch, depth is 12 inch, xi is equal to 2% MP. This, if suppose the machine is not mounted on the cantilever, then the cantilever is going to deflect under the load. The deflection under the load, we can also calculate it. So now, once we model it, we can calculate the stiffness T over L cube. You can get the number omega equal to K by M. We can get 1.6 hertz. Static deflection we get 0.024. And initial condition is static deflection is this and velocity is 0. This is the closed form solution where damped vibration can be written as undamped vibration 1 minus chi square. So we can write down the equation. Closed form equation is this. Okay, next. If you solve by finite element method, okay, next using fist. Next, Aniket, I get these two curve. One is an analytical solution, other is a fist solution. So they matches very well. So you can solve a single degree freedom system harmonic motion easily. Similarly, you can solve multiple degree freedom system also. Okay. Now, this is the single degree freedom system we are talking about. Now, in the last, we will be talking about the multi degree freedom system. And here I have taken two mass, two spring. The stiffness of the column, both the column is same. Length is 100 inch, and the mass is defined by the 6,000 pound and 3,000 pound. Okay, so we can find out the, and this problem, since it is a multi-degree system and two mass two spring system, in the last lecture we calculated the stiffness matrix after doing condensation of theta 1 and theta 2. Two rotations were removed, and a stiffness matrix in terms of the U1 and U2 were calculated, which was 48 EI 7L square 16 minus 5 minus 5 2 U1 U2. This is the condensed stiffness matrix where there is no rotation at all. If I take this and mass is 6,000 to 3,000, I get a eigenvalue problem, standard eigenvalue problem, and calculate the frequency and mode shape. Okay, next. Calculate the frequency and mode shape. I get the lambda 1, lambda 2, this, omega 1, omega 2 is shown here. F1, F2 I can calculate, 0.26 and 1.34. Similarly, period I can calculate. And if I substitute lambda 1, lambda 2 in the above equation, I can get the mode shape, which is 1. This is the unnormalized mode shape, 3.0055, 0.655. If I take on the left hand side, the first mode is plotted, where the mass 1 has a displacement, normalized displacement 1, and mass the top mass has 3.005. Similarly, in the second mode, we have a 1, and at the top first floor, we have unity, and the top floor 0.0655. This is the shape we have plotted. Okay, next. Now this is the equation. Now I am showing here. Further, I am because if I continue further, it is going to take a lot of time. So I will be reducing the time by doing the some simplified calculation, which I have described it here. Okay, so we get the frequency, two frequency and two mode shape. From that, I will use the generalized mass, and I will using both generalized mass, I can normalize the mode shape. First thing that you normalize the mode shape. Once you normalize the mode shape equation I have given, I can calculate the acceleration which is in this case also the acceleration is given zero point 0.1 plus ti e to the power 2 ti for a given value of damping into g. So the period we know, we can calculate both the acceleration, we can calculate the displacement because we know omega 1 and omega 2. Similarly, if I multiply the maximum displacement, we get gamma 1 is d1 and y2 equal to gamma 2 is d2. Similarly, gamma 1, gamma 2 I have calculated, which is nothing but participation factor. Using this, I can calculate the displacement vector u1, u2 vector, and then I can do algebraic summation, absolute summation, SRS solution. Similarly, I can calculate the mass coefficient S1, S2 vector, and the force coefficient. Once I know the force vector in first mode and force vector in second mode, I can calculate the shear force bending moment diagram, and this way I can design the structure. Thank you very much. This is in nutshell. If you have any question, please let me know. And anyone who wants to know further detail with example, or if you want to have a more discussion, you can have a discussion later on with me. Now there are two problems which we are going to solve it, which has been described. One is a cantilever beam using fist, which I have shown here, and the same thing Aniket is going to do the solution. Is one is a cantilever beam whose dimension I have written. The length is 80 inches, E is 30 into 10 to the power 6, B and D breadth and the depth is 2 inches, and I is we can calculate I and area cross sectional area. Density is defined 0.0072723 pound second square inch. So I can calculate EI flexure rigidity and omega 1 equal to 3.52 flexure rigidity divided by the m into square here. And from that I can calculate the frequency, which is omega 1 equal to 64.5 radian and f1 equal to I can calculate 10.26. Similarly, f2 can be calculated, f3 can be calculated, uh, and this mode shape also we have shown. Mode shape also we have shown 5.1, 5.2, 5.3, and in most of the analysis, one has to match the frequency as the mode shape when you solve using the FIST program. Particularly second mode, when there is a empty node, there is an intersection at 783, and at the third mode intersection is 0.358 and 0.866. How closely we are able to calculate using FIST this number. And the second example is a circular plate, which is again 80-inch diameter, thickness is 1 inch, E is given, mu is given, rho is same. So I can calculate the fundamental frequency, which is given by formula, and this has to match with the fundamental frequency which FIST is calculating. And then here the eigenvalue has two, here since it is a plate, a 2D structure where the plate can be described into R and theta coordinate system. So we have a mode shape which are related to nodal diameter which I have explained here in the first figure, m equal to 1, m equal to 2, m equal to 3. This is the nodal diameter. And then n, which is a nodal circle, is one circle, then intersecting with another circle, that is n equal to 1, and two more circle which is n equal to 2. These are the nodal circles. Then frequency has to be seen with given mode and nodal circle, which will be describing in the lecture given by Aniket. Now, Aniket, if any question is there, they can ask. Otherwise, you can start.
Hello, sir.
Hello, sir.
Kushwa sir.
Kushwa, sir.
Ah, yes.
Yeah. So these two problems we are going to solve in the second session. So you can we have 10-15 minutes more, so you can explain this problem as well as more shapes you can explain, so that in the second session we can have the hands-on.
I have explained both the problem.
Okay.
I have explained both the problem and the mode shape, so you can start. Start. Unless they have a question, if they have a question, or later on also, if they have a question, they can send it to me.
If anybody has any question, they can please ask.
Or they can ask later on also. You can ask any type of question. We have enough expertise in this area. There is no doubt about that. So any kind of problem we can solve using the FIST or any other package. Okay.
Anybody has any questions? I request you unmute and you can ask the question.
So at 12, the session will end. So in the second session, we can have the hands-on where these two problems we can solve. So for now, if anybody has any question, they can please ask.
Okay.
Right. So I guess if there are no questions, we will finish end this section. So on behalf of Automation Department at RIT, I would like to thank both the experts, Sri S.S. Tikwa sir and Mr. Aniket Desai for conducting this particular session. As discussed just now, we will be solving both these problems in piece in the session after lunch. So post lunch, we will have this particular piece demonstration of these two problems. So do we end the meeting now, Aniket?
Yes, sir. Yes, sir.
Okay.
Yes, sir. Yes, sir.
Thank you. Thank you.
Thank you, sir. Thank you all.
Thank you. Thank you.
Hello.
Aniket, that is closed now?
हो सर एकच मिनिट सर एकच मिनिट Yes, sir. We can close, sir.
Okay. Okay.
हॅलो हां सर ती आपली टीम्स वरती घेतली तरी चालेल. आता कसं आहे, आता कृष्णसरांचं झालेलं आहे, आपण आता हँड्स ऑन घेऊ शकतोय. तर मीटिंग टीम्स वरतीच घेऊयात, काही इश्यू नाही सर. ते पण आपलं लास्ट सेशनला पण हँड्स ऑनच आहे. हां ते कम्प्लीट फीस होऊन जाईल त्याच्यामध्ये. तर ते पण आपण टीम्स वरतीच घेऊयात. Okay, sir. Oh, okay.